third session out of the four-part series for commercial heat pump water heating, design, operations, and maintenance. My name is Armando Verdiel from Lighting Design Lab. Very happy to introduce us today. Evan Green presenting, as well as Lauren Baskar moderating. As you'll note, you're all muted. If you've been here for the previous sessions, you'll know the drill. You're all muted. However, please engage with us and ask questions on the bottom right-hand corner, or if you go to webinar dashboard, you'll see a chat or a questions drop down. Please engage us in chat, ask questions, drop comments, and we'll have dedicated times to stop and address these. A recording of this webinar, as well as a handout of the slide deck, will be available on the lightingdesignlab.com website on the education and resources page. So if you're looking for them, look for those there. Without further ado, Lauren, teeing it up to you.
Thank you. Great. Yeah, welcome back, everybody. If you were here for sessions 1 and 2, we're really excited here for session 3. Change of instructor from Colin Grist to Evan Green. Super excited, Evan, to see you here. And you're in the cold eastern side of Washington, correct?
Yeah, that's right. I decided to pick the coldest corner of the state to give the presentation today.
That's perfect. So there will be, we can talk about cold climates and commercial heat pump water heating, maybe. That's great. Today I'll be moderating. You'll need your smartphone. We run an app called Slido. If you were here before, you saw it. It allows us to take do some polling with you and find out who's in the virtual room with us. We love your comments and your questions that come through on the Slido app. The good thing about Slido is it collects no data. It won't spam you afterwards. It's very clean, so you don't have to worry about that. I always like that that bit. So yes, feel free to put your questions and comments in the Q&A tab. I'll be monitoring those throughout the session, and then have your smartphone ready and we'll do some polling. And with that, Evan, looking forward to today's session.
Yeah, thanks a lot, Lauren. So before we dive in today, I figured I might give you a little background about myself. So I am currently a research and design engineer at Ecotope, an engineering firm in Seattle, and we focus on energy efficient and decarbonized designs for plumbing and mechanical systems. So half of that is to electrify with current technology like heat pump water heaters, and the other half is to ensure that we're creating efficient systems that don't use much energy anyways, because we don't want to transition everything to electricity and then create an extra toll on the grid. So those are two things that we focus on hand in hand. So today we'll be focusing on the commercial heat pump water heating aspect of what we work on here at Ecotope. And some of the knowledge that I gained from this was actually from my previous position as an applications engineer at Colmac Water Heat, which is a heat pump manufacturer here in Eastern Washington. And that's how I found myself in this northeast corner of the state. So some of the key questions that we're going to try and answer today is, how do we actually choose the correct heat pump water heating equipment? So there's a lot of different applications that these can be installed in, and a lot of different geographical locations that certain equipment will work well in and then others may not. So you need to make sure you choose the right equipment for your location and size it and apply it correctly for the application you're going to be, or the building type that you're going to be putting it into. And the other key question we're going to try to answer today is, what steps do I need to take to implement a commercial heat pump water heating system? So these systems can be extremely successful, and we have a bunch of different case studies that show that this technology has really been proven out and can supply reliable hot water, but they can also be a huge problem and ultimately fail in the end if you don't go through the proper steps to design and implement them correctly. So the first way that they might not work so well is they just fail to start up as soon as you start the building up. Maybe something's plumbed wrong and they're not getting the water that they need. And the other way that you need to make sure they prevent them from failing is in the long term, right? These heat pumps can last 15 or 20 years, if they're installed correctly and properly implemented. But if they're designed in a way and the proper manufacturers and designers aren't consulted correctly, they might be put in a situation where they're just constantly turning on and off, and they can wear out really quickly. So you need to make sure that you take the steps to properly communicate with your manufacturer and designer and installer to make sure that these systems are going in correctly so that they can live a long and happy life. And so Lauren explained Slido pretty well in the beginning here, but I'll reiterate that we're going to use Slido as an application to interface between me and all of you. So any questions that come up, we'll take breaks every now and then through Slido, and I'll ask you some key questions to be able to get some feedback, so I might be able to provide a little more detail if anything's been left out based off what you are seeking to learn today. So we're going to use the event code design3 in our Slido, which you can access via slido.com on the computer, or you can scan this QR code on your cell phone. And you can just open up your camera and point it at this code here in the top left, and then it will open up this survey. So we can ask you a few questions and get some tailored feedback. So scan this QR code, enter design3, and then I'll give you a little while for the questions to populate and for you to get some answers in, and then we can start answering some questions and learn a little bit more about who's listening in today.
So Evan, while folks are filling in those, we can chat a little bit.
Yeah.
Sure. So you have been at Ecotope for a while and designed commercial heat pump water heatings for Colmac before then, yeah? And so not new to this game. This is your wheelhouse.
Yeah, right. I mean, straight out of college, I knew I wanted to do something to kind of bring together green technology and try to find solutions to answer some of the world's problems in decarbonizing our future. And so Colmac Water Heat was actually pretty close to the college I went to at Eastern Washington. So some of my classmates had minglings with some of the people at Colmac, and that's where I learned about them. And then that's when I kind of got immersed into this, new marketplace of this green technology that's actually been out for a long time and has been applied in many different applications. But now we're finding a way to most efficiently apply it to what we need here, which is, in Colmac's perspective, commercial buildings, right? And heat pumps have been applied to commercial and residential. But I've had a lot of fun learning about these different technologies and working with a bunch of different designers to try and figure out how we can make heat pumps work with their specific applications.
Yeah, that's super cool. Great. Well, we've got 19 folks in the room with us, and looks like people are still logging in and being able to chime in. I really do love to see all the different folks coming on board with us. Some really interesting diversity here. This session should be really great. Thanks for sharing a little bit about your background too, Evan. I always think it's always really fascinating to hear about your experience too. All right.
Yeah, I'm always happy to share, and I'm really happy to see we have a really good number of people turning out today. It's kind of that sweet spot where we have a small enough number of people that they can really give feedback that we can address, and large enough that we're still getting the information out and allowing it to spread. So we have engineers and operators and resource conservation or energy guy for a school district. That's perfect. So I think the information we're spreading today can apply to a really wide variety, and it looks like everybody that gave their feedback here will be able to get some valuable information here, because we're talking about the interface between the designer that's creating the design for these systems and the installers that are actually putting them in, and the importance of the continued operation of these systems for their efficiency and reliability. And we have a lot of novice and intermediate listeners here today, which is perfect. Hopefully I can spread some really great information. And if I do go too fast through any of this subject matter, feel free to drop questions in the chat as you have them, or we will be checking in through Slido, so you can give some feedback there where you might be able to bring out some more specific information. And then we have a small fraction of experts here. Hopefully I can still give you some good information here. And if you have any feedback on anything I'm saying or anything you want to add, definitely drop that into the chat, because I want to make this as full as possible. And of course, there's always something that I could miss in a 2-hour conversation. So muddy waters in this process, we have resistance from owners and engineers to basically spend all the extra money for these systems that are not commonly installed. Yeah, it seems risky since it's not something they normally do. Yeah, and that's really relevant to today, because the technology is there, but there's not a lot of designers and installers that have implemented it. So when you're installing these systems, that means extra time and money spent to understand how to do it right. And luckily with DNR, there's a lot more education coming out and content coming out fairly quickly to be able to address some of these concerns. And the next comment's about the same, that school districts reluctant to try something new. Yeah, and engineering firms not knowing about the heat pump water heating, either domestic or hydronic. Yeah, really common theme here. Sifting through integrated unit specs, generally confused. Yes, yeah, there's a lot of different information that doesn't seem to line up sometimes between manufacturers, but hopefully we can put those into more specific buckets that you'll be able to more generally look at a heat pump category after this. And the new Seattle Energy Code bans gas and electric resistance water heating, effective January 1st, 2022. So yes, that is, DNR is actually providing content to address Seattle inspectors on how to inspect these, which will then inform designers as well on basically all the boxes you need to check to get these systems in, as well as general design advice on how to make them apply to your building. And then heat loss on recirc is a big thing to tackle with these heat pumps, and there's several different configurations depending on your application that we can implement there. And equipment startup we're going to be going over today, as well as fuel switching is the big driver for a lot of these heat pump applications. So this is all really great feedback that we can definitely address in a lot of what we're talking about today. So this is really exciting. And great. So the first thing we'll talk about today is a case study of a system that has been successfully installed in Seattle. And this is one of many systems that Ecotope has designed and overseen the installation of. And we're getting really good savings and feedback from this building. So Jackson Apartments is a market rate building, and you can tell by the pictures here, we have a west building and an east building, I believe. I may have those directions backwards, but they're two side-by-side buildings with their own, each with their own central heat pump water heating system. And you can tell the architect put a lot of work into making sure that this building was aesthetically pleasing, as well as putting a lot of thoughtful design into all the landscaping and really the resident experience as they enter and live in this building. You can see these are all actually native plants that as soon as you step out of the building, you just feel like you're in almost an outdoor meadow or kind of in the middle of nature, even though you're right in the middle of city. So the overall theme here is we want to make sure, or the architect wanted to make sure, that the residents felt good here and that they were having a really positive experience. And given the rent in Seattle, you want to make sure that you're accommodating them with everything that you possibly can to convince them to live in a great city, but at a really high cost a lot of times. So market rate apartments we're making sure that we're giving them, even though this is a heat pump water heater system with the new technology, where it's not acceptable to, have days of cold water or anything like that. They need to make sure they have all the amenities plus some that they would expect with a more conventional system. So a little bit more nitty gritty into the mechanics of this plumbing system here. This is a new construction building, so we were able to work with the architect a little bit and provide enough mechanical room space for the most ideal heat pump water heating setup, which is always really nice in a new construction building. And we have 2 Colmax CXA15 water heaters in this mechanical room, and they're paired with 3 500-gallon tanks. So this will handle the full capacity of, this is the west building specifically, so this will handle the full water heating load. So these heat pump water heaters will continuously charge this storage to make sure that there's always enough hot water for the occupants at a really low energy use rate. We also have a parallel temperature maintenance tank, which is handling those temperature maintenance losses that were addressed in that feedback, because there's heat pumps have kind of a difficult time reheating warm water up to a really high temperature, as you would see with the water that circulates through the building. We send it out hot and it returns slightly cooler, and the heater has to reheat that to a high temperature to make sure that that water in that loop never goes cold. So we actually have designed a parallel system with a heat pump water heater that is specifically designed to allow those higher entering water temperatures and still operate efficiently. So you can see in this bottom picture, we have this small heat pump paired with this tank right here to handle those recirculation reheating loads. And then this has a backup water heater in case anything goes down in the system. We're not seeing cold water events. And this is all installed in the parking garage, which is giving a really, is providing a really unique condition for the heat pumps, because as the air passes through the parking garage, it actually warms up and it raises the minimum air temperature that these heat pumps will see throughout the year. And I'll go into that a little bit more in the next slide here. And because we implemented this heat pump system in this highly efficient building, we were able to see 15% annual energy savings of the entire building because we have such efficient water heating equipment here. Water heating is about a third of the overall, about a quarter of the overall building usage. So it makes a big difference when you're doubling or tripling the efficiency of your water heating system. And so here's a better picture of the outside of the mechanical room that these heat pumps are located in. You can see that this duct right here, this is actually the exhaust from the 2 heat pumps that are sitting in this mechanical room. And then the garage exhaust, you can't quite see in this picture, but it's located right next to that. So what's happening is we're 3 stories down in this picture. So we have air that needs to be pulled in through the heat pump water heaters, and the heat is extracted from that air to then use that heat to heat the water. So these heat pumps are consistently cooling that air down by pulling the heat out of it. So we want to make sure we're providing them with fresh air and the warmest air possible, so then they can most easily extract the heat out of that air. So if we're 3 stories down in a parking garage, we are actually drawing air from the outside in the entrance where the cars come in, and that air is working its way down the 3 different levels in the parking garage before it makes its way to this mechanical room. And what's happening there, and what that's allowing, is all of the heat that's been stored in all of the cement in the parking garage from, say, if we put some numbers on it, if it's 60 degrees in the middle of the day, that 60-degree air is coming into the parking garage, and some of that heat's being absorbed into the cement if the cement's cooler than that 60-degree air. But then at nighttime, that temperature drops down. It could drop down to 30 degrees, but now we have all of this preheated cement in this parking garage. So as that cold 30-degree air passes through the cement on the parking garage, it's actually going to absorb some of that heat back. So the heat pumps might see 40-degree air. And that makes a big difference with these heat pumps specifically because their minimum allowable operating temperature is 40 degrees. So even though we have a record low or a design low of like 26 degrees in Seattle, the entering air to these heat pumps has never dipped below that 40 degrees that they allow. So we have this constant airflow of fresh air outside passing through the garage and being heated up, and then that heat being extracted back out by these heat pumps as they transfer that heat into the water. Then that cold air is exhausted out of the garage where it's not going to be recycled by these heat pumps. So now we can talk about the flow of water in the system. And I mentioned that we have a recirculation heating system that's separate from our primary water heating. And you can see that here as the cold water supply comes into the building, it's being heated by these two primary heat pump water heaters. It's being heated from a cold temperature up to a really high temperature and then stored that way. And then this hot water can be sent to the mixing valve and out to the building whenever someone turns on a tap and needs hot water. In parallel, there's always water circulating through the pipes in the building, so then whenever anyone turns on a tap, they have access to fresh hot water. And if it wasn't circulating, the water in this pipe would cool down to an unacceptable temperature and cause someone to just have to sit there with their tap open for a really long time, right? If I know in my house, some people have a circulating loop in their house, but in mine, I have to run my sink for maybe 15, 20 seconds before I get hot water. But if you multiply that out to the size of a 300-unit building, someone could be running their tap for an hour before they actually get hot water. So we're circulating that, and as it cools slightly through this loop, it's being returned to the temperature maintenance system to be reheated up to that high temperature, so then it can send it back out to the loop. And this temperature maintenance heat pump is designed so it can heat that warm water up to the higher temperature in parallel with these primary heat pumps that can heat more efficiently, but they always have really cold water coming in. And that's a big requirement for some heat pumps altogether, while others are less picky about that entering water temperature. So they're both supplying the mixing valve in parallel, and anytime someone needs hot water, that extra hot water is coming out of the storage and being supplied whenever they need it. So the key takeaway in this system, as we've presented it here, is improvements in energy efficiency do not have to come at the sacrifice of comfort. We have a much more energy efficient system using a lot less power, but the occupants of the building would never know that it's this separate system. All they see is they turn on their tap and they get as much hot water as they need. I'll pause for questions here, so go ahead and open your Slido up and drop some questions in the Slido. And Lauren, were there any questions as I was going through that came through the chat?
No, we don't have any questions here through the question and answer tab, but this is to avoid confusion for learners. You could put your questions through the Slido, or you can put them in the Q&A bar, either way, as you wish. So there was a question, actually, I want to address this, and I'm hoping that Armando from Lighting Design Lab can answer this. The second session of our work for this training series has not yet been posted to the Lighting Design Lab website. So I've asked Armando, hopefully he'll be able to chime in there, but we're waiting to know when they'll post that. Should be soon.
Should be soon. Lauren, I'll ensure that if it's not late this week, early next week on the double. So thank you for that.
All right. And then I'll let you know, Evan, if there's any questions that come through the Q&A bar. Otherwise, I'll let you handle it here.
Great. Thanks, Lauren. Yes, we have a couple of really good questions already. What happens if the heat pump water heater gets air less than 40 degrees? Do they stop operating or just operate at lower capacity? And that question, the answer to that question really depends on what type of heat pump water heater you use. These Colmax we used here are R134A heat pumps. So those kind of bottom out at 40 degrees, and anywhere below that, the refrigeration pressures can't sustainably cycle through the refrigeration cycle. I won't go into exactly how that works, but the short answer there is the heat pump will shut off to avoid damaging itself at these lower temperatures. Other heat pumps may handle lower temperatures a lot more easily. They will still operate at a reduced capacity because it's harder to take that heat out of the air. And how do you control flow from primary tank versus temperature maintenance tank? Maybe I'll scroll back to the previous diagram after we make sure no more questions are coming in, but the gist of it is that temperature maintenance tank, that we have kind of two loops in parallel, and it works out so the primary storage only supplies the water to the residents that are actually opening the tap and pulling that hot water out of the system. Because if 5 gallons comes out during a shower, then you have 5 gallons of cold water only entering that primary tank, right? So it's 5 gallons out, 5 gallons makeup coming in, while the temperature maintenance tank has that loop water that's consistently circulating, and that doesn't really have the chance to return to the primary storage. So they kind of balance themselves out because their inlets are only allowed certain flows. And I would like to see a cost comparison between this system and a natural gas system. Yeah, I think that's information that I'm not working on personally, but we are working on to get a better comparison of that, because that's a big pain point here, right, is the comparison between gas and electric. And there's a lot of different factors. One being if this is the last system that's using gas, the domestic hot water system, then you may be able to take the gas infrastructure out of your building completely if you implement an electrical heat pump water heating system, which then makes it pencil out really well. It gets a little bit more muddy if you're just comparing a gas boiler to a heat pump water heater, and there are different sizing methods and capacity requirements assigned to those. Yeah, so with that, I think I'll take I can't scroll back, but I hope I answered the question about those two parallel flows, and feel free to ask any clarifying questions as we move on here. Okay, so a bird's eye view of what we're going to talk about today is where we're basically looking at the transition between having a design come in from an engineer and transitioning that design to a proper installation that will operate really well down the road, right? So you might see this as being the primary role of a plumbing contractor that's receiving the designs from the designer and making sure all the details are right to ensure that you can actually install this equipment properly. So the first step here is finding subcontractors with the right values to be able to install this equipment, and we'll talk about the attributes that would be good to look for in or convey as a contractor that can potentially install this equipment. The next thing we'll talk about is the details that you need to consider when you're purchasing the equipment, and the details that you need to make sure line up between the design and installation, and make sure the details of the equipment line up with the desired details that make that design work. And then we're going to talk about the verification and purchase of the equipment and what that might look like between the equipment rep and the manufacturer, and what information you might want to elicit before you purchase this to verify that everything's lining up. And then finally, we're going to go through kind of an installation light version. So it's really high level of what you need to consider when you're installing this equipment, and kind of what you need to keep in the back of your mind, as well as how you can ensure successful startup of the equipment. So the first thing we're going to do is find our subcontractors and talk about what you might want to convey if you're the subcontractor bidding for a job like this. Right, so the first thing everyone thinks about is the experience that a contractor might have with heat pump water heaters, and in terms of gauging how successful that job could be and how they might be able to anticipate different issues that might arise. And you'll find that there's a lot of contractors that haven't installed this equipment before because it's a relatively new to this market. You know, everyone's installed a gas boiler as a plumbing contractor, but there's a lot fewer that have installed a heat pump water heater. So I don't think it should immediately take that contractor off the table if they haven't installed a heat pump water heater. I think what you should focus on is how eager they are to learn about this new technology and what their viewpoint is on this technology. There's some contractors that, you know, they just keep saying, well, we should have just put a boiler in. There's all these issues to consider with heat pumps. We know how to put boilers in, just put a boiler in. But there's others that are eager to learn about the technology, and if you have that mindset as a contractor, your job's going to go a lot more smoothly, as well as the ability to communicate and freely ask questions. If you as a contractor, or you're looking for a subcontractor that says they already know everything about heat pump water heaters and we don't really need to open this dialogue, then that might set off kind of a red flag, because there's always more to learn about this evolving technology with new manufacturers coming out. So the next step here is having open communication, as a contractor or as a designer, or really anywhere in this process. You need to make sure that you have open lines of communication for a successful install. Excuse me. So the first part of this communication, and something really important here, is education of these systems is key to properly implement them. Right, so there's a lot of different channels to learn more about heat pump water heaters in general, as well as documentation and webinars from specific manufacturers if you already know what manufacturer you'd like to go with. So DNR, as I've mentioned a couple times now, has created a lot of material working with myself and others at Ecotope to talk about the general considerations of heat pump water heaters and more clearly explain the different types of heat pump water heaters and how you can apply them. But you also, in addition to learning about them in general, you can talk to manufacturers, and a lot of the times they'll have their own design materials with specific details that you need to consider for that manufacturer, as well as the manufacturer's rep have details that would really help if you open a conversation with them and bring your design forward. And then you definitely need to talk to the engineer and have them walk you through the design as an installer. And so any questions that come up there, definitely ask as many questions as you can. And if the engineer has a hard time answering questions, or they don't quite understand how a certain part's working, that's when I would highly encourage that you talk to the manufacturer alongside the engineer and get any of those questions answered. So the next step here, after you fully understood the design and opened a dialogue with the designer and manufacturer, is going to be select the actual equipment you're going to use. So usually there's a basis of design of a certain piece of equipment that the designer has created their entire design around, but you want to make sure that there's several manufacturers that might fit that intent. So you want to make sure that you're picking the right manufacturer in all the other considerations of the design, like lead time and accessibility. So if you're looking at this basis of design and you see a Colmac heat pump water heater, for instance, and maybe there's a few different water heaters that or maybe an alternate water heater that you've used before and had a lot of success with, then it is possible to propose a different manufacturer, say if Colmac's lead times are too long or something specific. I'm not picking on Colmac, but just using them as an example. So you want to make sure that whatever manufacturer you're looking at still conforms with that design. We mentioned Colmac in the Jackson Apartments case study, having a minimum air temperature allowance of 40 degrees. So if this design had the heat pumps located on the roof, or there wasn't this garage buffer, then you wouldn't be able to just drop Colmacs in and have them operate successfully, right? So if they specified a heat pump that was meant for that cold air, you want to make sure that this new heat pump you're proposing will fit with that cold air and that piping configuration. For example, we had the high entering water temperature capabilities of the heat pump that heated that recirculation water, right? And then sometimes definitely just easiest to go with the basis of design, but sometimes the lead time and the availability of that specific equipment is challenging. Maybe they don't even offer that model anymore, and now they have a new generation. So you need to make sure if any details have changed between one generation to the next, you need to make sure to implement that into the design and installation considerations of the heat pump. So one piece of advice from me, as based off my experience as an applications engineer for a manufacturer, as well as a designer here at Ecotope, is support from a manufacturer is often more important than a lower price on a heat pump water heater. And that's because if any of you have gone through a submittal package, you know there's some of these submittals are kind of clear as mud. So there's some information that's not going to present itself clearly that you will definitely need during the design or installation process. And there's certain feedback that is really important to get from the manufacturer based on any unique designs you're implementing that aren't straight out of their book. Right, so if you have access to this manufacturer at all times, that will definitely save you money in the long run, because you're not going to be issuing change orders and not going to be doing rework because there was some piece of information missing in the initial design and installation. So now we'll check in here, get some feedback from you guys. What experience do you have with these first steps in the process? And this is just a simple level of experience, but if you want to put anything in the chat or the Q&A, and maybe share any weird situations you've been in based off these steps, and any big pieces of advice based off what I've given here, that would be great to hear. Great, so we have some that have dabbled and some that will take these steps soon. So hopefully I've gotten some information out here that you might not have thought about and will make these steps a bit easier. So with that, I'll move forward, and yeah, feel free to drop any questions in the Q&A as I go forward here. So in considering the main pieces of equipment that you'll be installing in this water heating plant, the main components here are the heat pump and storage, and the controls to allow the heat pump and storage and the rest of the system to talk to each other, and then the mixing valve. And there's an order to choose these, and I'll go through why that is. So the first that we're going to figure out is the heat pump and the storage. And that's because we want to make sure that the heat pump isn't being shoehorned into a design around the rest of the system. We want to make sure the water heating system is doing everything it can to accommodate the heat pump, because this is kind of our high dollar item, speaking literally and metaphorically, because this is what's saving us all that energy and providing the hot water. So you want to make sure it's reliable, and you want to make sure it's efficient, and selecting the components around your heat pump water heater are really going to help ensure that. So when choosing a heat pump water heater, there are quite a few available products on the market, and it is a quickly evolving market. So I would urge you to not just save this image and reference it in a year, but this gives you a good idea of what's available today and what kind of more general categories we can put this equipment into. So the first category that we've created here is the multi-pass integrated heat pump water heaters. And they're more specific to residential or very small commercial applications, simply because they don't have a really high recovery rate or really high capacity. So they're more suited for residential or small residential applications, right? And these heat pumps have everything built in. They have the storage and the heat pump together, so you don't have to worry about the extra plumbing. So this heat pump is one more like you would see being sold at a big box store and installed maybe in your garage or in your basement to heat your water with. The next product category is the single pass CO2 heat pumps. And we put this in a category by itself because they have some pretty specific capabilities compared to these other more conventional refrigerant heat pump water heaters. And they can operate in really low temperatures because of how their refrigerant works. So the Sanko 2 and the Mitsubishi pictured here are both designed so you can just put them directly on the roof, and then you can plumb the water in and out of the heat pump and to storage tanks in the mechanical room. So really convenient for rooftop or outside installations where you don't have that garage or buffer space that you can put our third category into, which is a single or multi-pass R134A heat pump. So these are kind of more larger commercial heat pumps. You notice they're the same refrigerant as these smaller residential heat pumps, but they have a much higher capacity and they have that ability to stand alone on their own, like this second category of CO2 heat pumps. So these actually originated in Hawaii. So they were designed to just put on the rooftops and buildings in Hawaii and always operate in 70 or 80 degree weather. And they operate really efficiently there. So more tropical installations outside really make this equipment shine, but they can also work really well in applications like Jackson, where they're in a semi-buffered space so they don't see air temperatures below about 40 degrees. And here's a little more detail into the refrigerant temperature ranges and what's available out there in terms of refrigerant. So CO2 is what we mentioned first, and you can see the temperature range of CO2 refrigerant in general is down to about -10 degrees. So with a 26-degree design day in Seattle, there's a huge buffer there between your heat pump not running and your minimum temperature. Even if we have a crazy record low and your heat pump's on the roof, it's still going to run just fine if it's CO2. There's also upper temperature limitations that you need to tune in with the manufacturer a lot more closely on, because there's the general limitations we have pictured here are about 100 degrees for CO2, but manufacturers kind of make special tricks with their refrigeration circuits to mitigate those limitations. So the manufacturer will have a much more granular min and max temperature range that these units can handle, but these areas are kind of where these refrigerants shine. So R134A, you can see bottoms out at about 40, and then in really high temperatures, it does really well because it has low refrigerant pressures. And then R410A is an option offered by Colmac as a heat pump water heater, but you don't see it a lot in actual heat pump water heaters, but it is, I would say, by far the most common refrigerant in hydronic heating applications and air conditioning applications as well. So that can go down to really low temperatures as well, and it has kind of a middle pressure compared to CO2. I see we might have do we have a question, Lauren, or? Sorry.
Yeah, the question is whether all Colmacs that are being used are R134A refrigerant.
Great, yeah. So the majority of them are, but we also have this R410A option from Colmac. The CXV5 specifically is the current option, and it's a little smaller compared to the R134A options, but it's been really widely applied to a lot of areas in Washington, Oregon, and California to a lot of success.
And then we have some an interesting clarifying question, and Ian, I asked you to maybe clarify your thought here, but I'm wondering if, Ian, your question isn't, is there a difference in the refrigerant used between single pass and multi-pass heat pumps? Is that the difference, that the refrigerant itself is the difference?
Yeah, that's a big part of it, right? Because CO2 has a really weird operating cycle that I won't try to explain here, but because of CO2's characteristics, it does not, those heat pumps do not like to see high entering water temperatures. So CO2 is kind of off limits for multi-pass heat pumps. R134A, on the other hand, handles those high temperatures and related high pressures a lot better. So you will see the multi-pass options on the market are primarily going to be R134A, or possibly their near future synthetic replacements, right?
Okay.
The other thing, you can't just say if you have an R134A, it'll be good for multi-pass, because their components have to be sized differently as well. So you definitely need sign off from the manufacturer that this will work in a multi-pass configuration.
Okay, so that's really good to know. Another question from Emily, which is a great one. For each of these types of refrigerants and products here listed, do we have a listing of the maximum water output temperature, or are we going to cover that later?
I don't think we'll cover that specifically, the maximum leaving water temperature. In general, CO2 has, in general, a higher leaving water temperature across the entire temperature range, but that's something that is worth putting together on our end, so we should take a note of that for future content, as well as something that the manufacturer can really readily supply. So be cautious though. If you have a max leaving water temperature of, say, 180 degrees, as you know, Colmax CXAs have that, but they only have that if your air temperature is somewhere between 60 and 70 degrees, right? So if you rely on your system making 160, 170 degree water, you need to make sure that the air temperatures are actually accommodating the heat pump's ability to do that.
Very interesting, that correlation there. All right, all the questions. Thanks there.
Yeah, great questions. And so talking about that's a really good segue into this next slide, actually, because this is illustrating how the air temperature actually affects the heat pump capacity. And intuitively, it makes a lot of sense that the colder the air gets, the more difficult it is for those heat pumps to actually pull heat out of that air and put it into water. They have to do more work to do so. So a lot of manufacturers will come out with these capacity charts, or sometimes tables. And what you'll see oftentimes is the x-axis here shows what air temperature they're operating in, while the y-axis shows their BTU capacity, right? And you can see, depending on what leaving water temperature you're creating in this chart specifically, you have different capacities, as well as in different air temperatures. As your air temperature increases, your capacity increases. This CO2 heat pump graph is a little different, and it gives even more information, being you still have the intake air temperature on the bottom axis here, so you can see as the temperature increases, the capacity also increases, right? So that makes sense. The other thing we have here is a line that signifies the entering water temperature of the heat pump. So for this CO2 heat pump, if you have 120 degree entering water temperature, your capacity is greatly diminished, because the heat pump's basically turning itself down to protect against any adverse pressure or temperature effects from this high entering water temperature. So if you're expecting this 195,000 BTUs because your design temperature is 60 degrees, but you're feeding your heat pump 120 degree water, now you're only getting about 70,000 BTUs. So you need to be really careful of that when you're selecting the heat pump, and get a good understanding from the manufacturer on what those limitations are and what's driving that. And the other thing to consider here that's not pictured in either of these graphs is going to be the defrost D rates. As soon as it gets about below about 50 degrees outside, the heat pumps will actually start building frost on their coils. And that's because the air coil that pulls the heat out of the air gets much cooler than the surrounding air. So even if it's not freezing outside, you'll still see frost on the heat pump, and it has to go through a cycle to melt that ice off. As it's melting the ice off, it's not creating as much heat because that coil that has been employed to pull the heat out of the air is now just focusing its energy on melting the ice off of itself rather than pulling that heat. So the defrost rate is a really important factor in determining whether your heat pump actually has enough BTUs at your minimum design temperature to accommodate the water usage it needs to.
There's a quick question clarifying here, Evan, before you change slide. And I was trying to look here. Is it supposed to be a dry bulb temperature, not a wet bulb temperature? On the graph on the left?
Yeah, so yeah, that's kind of an interesting one because heat pumps do rely on, or the amount of moisture in the air does affect how much capacity a heat pump has, because the more moisture there is in the air, the higher capacity the air has to hold heat, right? So if you have a high wet bulb temperature, as this manufacturer has pointed out, that means that you have a high humidity and more moisture in the air, which will allow your heat pump to have a higher capacity. If we were to go off dry bulb temperatures, then this would rely a lot more directly on the dry bulb temperature and the humidity, because the combination of those two are going to drive how much heat is actually being held in the air. So the wet bulb temperature kind of takes that out of the equation because it's a better indicator of how much moisture is in the air. The CO2 manufacturer here has a D rate for relative humidity specifically. So it gets a little weird there because, okay, I know my design temperature is 26 degrees, but how dry is the air going to get at that point? And so, yeah, it's definitely worth thinking about.
Great, thank you.
And so now that we've talked about heat pumps, and hopefully I haven't confused you too much talking about the different capacities and relative humidities and refrigerants, we can talk about pairing storage with these heat pumps, because the storage not only provides a lot more capacity to the residents whenever they need hot water, it also provides the most ideal conditions for the heat pumps to operate in, right? Because these heat pumps I mentioned, they like pulling in really cold water and outputting hot water, and the storage, the way we set it up, will be able to drive that a lot more efficiently and allow these heat pumps to always bring in that cold water, and also have nice long run times that heat pumps like to have, because they don't like turning on and off really quickly. So that's why we have all this big series of marshmallows that are our storage tanks, is because we want to make sure we have enough capacity, as well as supplying those heat pumps enough time to fill all that storage so they run a really nice long time. And it takes them a while to settle out after they turn on, so then they're seeing the most efficient conditions they can. And when it comes to connections on these storage tanks, it's really important to think about where your pipes are going. So some heat pump manufacturers offer specific storage tanks as a part of their package, like Sanco 2 sells tanks with their heat pumps, or previously Sandin. Other manufacturers might recommend where to put the connections, but you need to be cautious here when you're buying tanks of where these connections actually go. Right, so we have three options here of what I've seen in the field, and I will preface this with saying that this option on the right is the most ideal based off what I've seen. So I'll actually start here and then talk about why the other options might not be as ideal. So here we have, you can see there's a really stark contrast between this blue section on the bottom and this hot section on the top, and that's because we are using stratified storage, which allows us to have this really hot water sitting up top, and then this really cold water in the bottom. And then we can pull that cold water out with our heat pump water heater and then heat it to a high temperature and then eject it to the top of the tank. So we have this really nice separation of hot and cold with really a small layer of, we call it a stratification layer, between that hot and cold volume of water. So now this heat pump's always seeing the cold water until this tank is completely full of hot water. So the proper connection locations here, we have all of our cold connections right on bottom because we're trying to keep that cold water right on bottom, while we have our hot connections right on top. We have the connection from the heat pump entering this tank horizontally. So then if it's shooting hot water in here, it's just shooting it in a horizontal motion. So it's not, well, my laser pointer is red, so it's hard to point out, but if it was shooting right in the top here and most of this tank was cold, we would have that jet of hot water trying to shoot to the bottom of the tank and mix in with this cold water. We don't want that. So we have a high hot heat pump location, cold low connection, and then dedicated entering and leaving water connections for the tank. So now our heat pump is separated from anything that's happening when it comes to water draws in the building. So it sees really consistent temperatures and flows as soon as its own pump turns on to draw from this tank. And so something that is a little bit less ideal in the middle here is we still have separate heat pump connections. We have cold connections on the bottom, but oftentimes a stock tank is going to have this second connection not very far up the side of the tank. So if you're trying to dump hot water right in the middle of this tank, which is really close to this cold water, then you'll have this mixture of lukewarm water in the middle and then hot water on the top. So your effective storage capacity goes down a lot because now you don't have all this concentrated hot water that can work its way all the way down the tank. You have this weird mix of hot and cold in the middle that's not going to be as effective at serving the occupant's hot water. And then the last connection that I've seen in the field is connecting the heat pump line straight to the hot water outlet, right? In theory, you would think this would work really well because our heat pumps are actually producing a specific water temperature independent of the entering water. But in practice, anytime the heat pump turns off, there is a segment in time that this line will just cool down. And while the heat pump's off, there's no water flowing through here, so you get a cold line of water. So every time your heat pump turns on, it's sending that hot water directly to the outlet that's going to the mixing valve. So there is a short period of time before your heat pump warms that loop up all the way that your occupants are going to see cold water if you eject your hot water straight to the outlet here. And we'll go through this animation, and then maybe we could take a 5-minute break so you can think about everything that I've gone through and see if you can come up with any clarifying questions or anything like that. So here we're going to look at an animation of 2 storage tanks in series. So then we can look at how the tanks actually stratify and pump hot water in through the top. One thing I want to point out here with the in-series tanks is you can picture this as one tall, narrow storage tank because the bottom of this first tank is connected to the bottom of this second tank is connected to the top of this first tank. So if you plopped this tank right on top of this next one, you would have the hot water in the top of this tank and the cold water in the bottom of this tank. Right, so, and another thing to point out here is we do have, for simplicity and animation, we have this heat pump outlet tied in next to the mixing valve, which goes against what I just told you about separating those connections. So take this connection with a grain of salt, but it still illustrates the stratification in these tanks really well. So first, if we start with cold tanks and start charging it with the heat pump, we have the hot water work its way down the second tank and then work its way back down the bottom of the large tank, which is actually this first tank. As soon as that hot water makes it through the entire system and all the cold water has been sucked out of those tanks and heated, it reaches the heat pump, and the heat pump knows the tanks are charged because it sees that high entering water temperature. So the heat pump shuts off, and then say morning time comes and everyone turns on their showers. So cold water is drawn into the bottom of this tank series, and hot water is pulled out at the same time and sent out to the mixing valve. As soon as that slug of cold water reaches the sensor that's attached to this heat pump, it sees a dramatic decline in temperature because we have those two separated volumes, right? So as soon as this stratification layer passes this sensor, the heat pump sees a quick drop in temperature and it says, I need to turn on and recharge these tanks. If the heat pump's not keeping up with the building draw and more water is being drawn out of the tanks than the heat pump can supply, this storage still continues to draw down until this peak load in the building subsides and the heat pump can now recharge the storage after everyone's done with their showers and there's lower usage. So then we have the completion of the cycle again because the heat pump's been allowed to recharge this storage and turn off seeing that high entering water temperature. So at this point, maybe we can pause till 11:05 and I'll leave it on this screen here, and feel free to come back with any questions about what's going on here and why we're putting the storage connections where they are and how they can best accommodate these heat pump water heaters.
Hey, Evan, I've got 11:02. Can we give folks 5 minutes so we'll come back at 11:07? Does that work?
Yep, sounds even better.
Perfect. All right. See you soon in 5 minutes.
Great, thanks. Okay, it looks like it's 11:07. And do we have, Lauren, do we have any questions
Yeah,
in the chat?
we do. We have a couple of great ones. So Aaron writes, when the storage tanks are nearing the point of being fully replenished, does the increased entering water temperature to the heat pump water heaters cause any issue? So I'll stop there. And then there's another clarifying question of, for single path operation, would you want to maintain a minimum lift, right?
Yeah, so that's a great question, and there are different ways to handle that. So the short answer is yes, it does cause a high entering water temperature at the end of run if you signal the heat pumps to turn off once these storage tanks are completely full. So depending on the limitation of the heat pump water heater, you might turn them off when there's still a little bit of cold water left in this tank, right? If you have a separation of hot and cold volumes and your 140 or 150 degree water is, has worked its way down to 3/4 of the way down this first tank, you're still like 7/8 full in your full storage capacity. So if you turn off when this water is maybe just slightly warm or even still cold, but you turn off based off a sensor up here, then you can mitigate any challenges that that specific manufacturer has with high entering water temperature. Otherwise, you do see a lower efficiency in these heat pumps that can still handle the higher entering water temperatures if you turn off later, but it's just that really small fraction of time where your storage is completely charged and your heat pump's about to shut off. So in the overall scheme of things, the efficiency bump or the efficiency hit you would see from that is really negligible.
Great. Okay, there's another question. Joseph writes, maybe I missed this, but what is the custom top connection referred to? The connection to the top of the tank as shown in this diagram, is that an option on manufacturer tanks?
Yeah.
It must have been one of the diagrams. I don't know which one he was referring to when he wrote this, but.
Yeah, so a lot of times we will see tanks that are a lot more like this as a standard tank. Maybe this middle connection here is actually located down here, so which is not ideal for a heat pump. So the custom top connection that I would refer to is having a heat pump connection up here as close to the top of the tank as possible in this horizontal manner, while you still have a top connection that can send hot water out to the building. Right, so you have 4 connections total on this tank, where in some tanks you have 2 and some tanks you have 3. The Sanco 2 tank already has these custom connections, so you can just buy that as a heat pump water heating tank and you're covered there.
All right, great. Those are the questions in the chat. Thank you.
These have all been really great and applicable questions, so keep them coming if you have any clarifying questions or want any more information about this stuff. Yeah, so tying that in-series storage concept to a real application, here is the storage at Jackson that we took a peek at with our first case study. So you can see these 3 marshmallows here are the insulated primary storage tanks, and you can see the top of this first tank is connected to the bottom of this next tank, and so on. So, and then the top of this tank is supplying hot water to the building. Now, when we're talking about these connections, this is a good time to point out that the connection charging this in-tank series is about halfway up this last tank. So most ideally, we would have that location up here, but the contractor selected more standard tanks, so this is what they got for it. So really, we're charging from here. So this last 1/6 of storage capacity could possibly be serving mixed storage water to the building. And we sized enough storage for this building that it was very conservative, so we haven't seen that happen. So we're still good there, but something to point out in this picture. And so now that we've selected our heat pumps and our storage tank, now we need to take a critical look at controls and what's going to be telling these heat pumps to turn on and off. And controls are really important and will vary depending on the heat pump water heater manufacturer you choose and what design you are implementing it into. So the main goal of your controls are to fulfill the design intent, right? You want your heat pump water heaters to turn on at the right time and to turn off at the right time to, one, maximize efficiency, and two, create as much hot water as possible while doing so. So there's a lot of different ways to implement these controls, and I will get into a little bit more detail a little bit later today. But you want to keep at a high level, you want to keep the heat pump water temperatures and the on and off set points, as well as the piping configuration and the locations of the temperature sensors in mind while you design your control sequence in coordination with the manufacturer and designer. And the last thing we'll choose here is the mixing valve. And you might find a little comfort here because the mixing valve in a heat pump water heating system works exactly as it would in a boiler system, right? It's taking hot water from the storage tanks, mixing that with cold water from the city, and it's sending that out to the building at a mixed temperature. So there's nothing really special about these mixing valves that are different with heat pump water heaters, but there's considerations that you still want to take to make sure you're choosing the right mixing valve regardless. And one of those considerations is the min and max water temperature, or minimum and maximum water flows that the building will see, because these mixing valves have a minimum flow requirement that if the flow dips below that, it will no longer provide the right temperature to the building. So it's really important that your circulation loop that's constantly pumping can satisfy the minimum flow rate that your mixing valve requires. So then you can always provide the right temperature to the building. And the amount of controls and monitoring that you're going to have associated with your domestic hot water design can really fit well into your mixing valve selection as well, because there's a lot of electronic mixing valves on the market now that have their own sensors incorporated just for their own, just to be able to run themselves. And so they can often report the temperatures and flows from those sensors to a monitoring system if you want extra alarm capabilities or something like that. And then the level of precision in the water you're supplying is another good consideration with these mixing valves, because in certain applications you want a really tight tolerance on the water temperature you're using. So that might be better applied to an electronic mixing valve that can hold those tighter tolerances. And then the last thing that you'll select here are the normal plumbing fixtures like Y strainers and check valves and things like that. Just because they don't have a crazy long lead time, they're usually readily available, and there's nothing crazy about the plumbing fixtures you're selecting based off your heat pump water heater design. So you do want to make sure that you're matching similar metals. So you want to make sure you know what the connections look like on your tanks and your heat pump water heaters. Then you select the right components and don't have mixed metals or mismatched sizes. But other than that, it's just it's your basic selection as you would have with any other system. And with that, I'll pause for a check-in here and ask what your key takeaway is so far in this conversation.
Yeah, Evan, as we wait for folks to chime in, one of the things I love about this class is that it is so based in kind of the real life how this rolls out. You know, it's not all in theory necessarily. It's a lot about on the ground and that kind of thing. What really happens and what relationships really need to be formed, and what really happens when you're planning or implementing your system. So I really do love that about this course.
Yeah, I was happy that was a part of this course as well, and that was probably one of the most interesting parts about being an applications engineer at Colmac. Is I worked with designers to talk about the high-level design concepts, but then I heard from the contractors that we're actually trying to put it in and getting their feedback, like, how the heck is this going to work? So I was able to see it from both sides and then understand the importance of having a dialogue between those two And so those things can be discussed before the contractor's calling and asking how they need to redo the system to make it work.
Yeah, it's the theory and the application. Great. I'll let you take a look here.
Right. Really go over the engineering. Case in point, the contractor's tank selections. Yeah, for sure. So the submittal process for that reason is really important as well, to align the contractor and the designer. Hopefully, and we got to keep in mind this is new to contractors and designers. So if you're a contractor that has learned a lot about these systems and you see something where the design could be improved, or you see some potential issues, that is really important to communicate with the engineers so you can both get on the same page early on in the process. And how complicated temperature is to functioning it correctly. Yeah, so there's a lot of different heat pump configurations that you can employ based off the temperatures that those heat pumps can handle. So I assume that was based off the heat pump water heating allowable temperatures. And the importance of a knowledgeable commissioning agent is really important here. Yeah, they should be involved really early on so the installer has a good idea of what they'll be looking for, and ensuring that the heat pump water heater can actually operate efficiently as it was designed. And configuration counts for sure. I covered that with the water temperatures, but yes, that is a huge point here. And you need to configure the piping around these heat pumps so they can operate most effectively in their application based off their specific needs. And seeing the sequence of cold and hot water going through the system. Primary storage tank being big enough not to send cold water back to the building if the heat pump capacity can't keep up. Yeah, exactly. If everyone turns on their showers at the same time and taking their morning shower before work, you need to make sure that that storage has enough water in it so we can actually supply the residents with what they need. And tank connections are extremely important. And a readable SOP is super important as well. Yes, and go over the engineering and tank connections again. Yeah, you're getting really, really solid points out of this, and I hope that we can continue to provide you with some important information. Yep, not rocket science, but it does require some attention to detail. I think that should probably be a subtitle on one of our design deep dives. That is right on. And then now we can go into a little more detail about the controls and conversations that will occur between contractors and designers and manufacturers, and the importance of all of these. So controls are very important because even if you have a system that's piped perfectly and a heat pump water heater that is super efficient, if the heat pump is not seeing what it needs to see or being told to turn on at the right time, none of that matters. It could just short cycle, turn on and off rapidly, or just not turn on at all. And then you could have cold water complaints or premature heat pump failure if all of this isn't figured out. Right, so a couple of things we need to think about when defining controls is, if we're talking about the actual controls hardware, what is needed beyond the equipment that's been specified? Right, so some heat pump water heaters can control themselves solely off of their own supplied sensors, so there's not any actual additional hardware that's needed, while others, depending on the engineer's control sequence that they desire, might need additional modules to tell the heat pumps when to turn on and off. And we'll define those three different categories a little bit better in a second here. But the other half of this is who's actually going to install the controls. The plumber is buying the equipment, the electrician is wiring it up, but then there's this low voltage wire that needs to be ran between the tanks and the heat pumps, and potentially to the communications in the building. So do we know who's actually going to put that in, and if they understand the sequence of operation for these heat pumps? And a key question to ask yourself before installing this system is, based off the sequence of operation, could a factory technician start up this equipment without making any assumptions? So usually it's a factory technician that's starting the equipment, and they need to enter the settings into the heat pump based off how the heat pump's working with the rest of the storage and everything else in the system. So is the sequence of operation that's written on the drawings, is that going to cover all those set points that that technician actually needs to put into this heat pump? Or will they need to guess at a few different settings that weren't really laid out by the designer? So you want to make sure to collaborate with the manufacturer early on in the design and the installation detailing process to make sure that those small setting details are ironed out and that the sequence of operation can actually be satisfied by that heat pump's settings and requirements. So there's 3 different tiers of controls that we can talk about, and they vary depending on how much responsibility the heat pump has. So internal interface is when the heat pump does all the work, versus heat pump and building management system interface, where they're both kind of working together. And that varies up to an external interface, where an external controller is doing all the work and simply just telling the heat pump when to turn on and off. And so a little more detail on the internal interface. I mentioned the heat pumps control themselves completely, so there's nothing external to the heat pump that's telling it what to do. I should say there's nothing intelligent telling it what to do, because these heat pumps will oftentimes be supplied with their own temperature sensors that will run to the storage tanks. So the Colmac here has 2 sensors that can run to 2 different locations in the tank, and you can enter settings right on the touchscreen here that tell it when to turn on and off based off those sensors. So you don't need anything external to the heat pump itself to ensure that it runs correctly. So it has its own sequence of operations that's based off those tank temperatures and the water temperatures that you set it to. And the second tier here might be, it usually involves the internal heat pump operations running itself. So the heat pump still uses its own sensors to determine when it's going to turn on and off, but an additional piece of information here, or an additional piece of hardware, might be an external building management system that simply wants to monitor the system and know how it's doing, and in some cases tell it to turn off when it doesn't need to be in use. Right, so the heat pump will still turn on and off based off these tank temperatures, but now it's telling this main building management system, okay, I'm running now, this is the temperature I'm making, and this is how full the tanks are. And then sometimes the management system can say, well, this is a commercial building and we're closing down for the weekend or for the week or whatever, so don't bother running for the next 2 days, no matter what your tank temperatures are. And then the third controls option here is an external interface. So that is when this heat pump is blindly going to turn on and off when it's told to turn on and off. It doesn't have any idea what's going on inside the tanks or anything else. It's just receiving a simple on signal from this external controller that is then much more intelligent. Right, so this is what's happening at Jackson, because we did have a remote backup electric heating just in case there's an equipment failure, because this equipment was installed early on in its generation. We wanted that redundancy there. So we had the controller designed by the manufacturer rep that also sells controls. So the rep knew exactly how these heat pumps worked as part of these systems, but they were able to design a controller that implemented lead leg and staging and implemented the backup electric heating in case there was an equipment failure, as well as communicating different temperatures and the overall status of the system. So there's a big advantage here in that the external controller can satisfy as complicated of a sequence of operation as it needs to, but the disadvantage is whoever's designing those controls really needs to know what makes that heat pump tick and how this heat pump operates most efficiently within the rest of the system. So not all controls contractors know that about heat pump water heating systems. Some may just set them up like a gas system, which could be a point of failure. But others can, go above and beyond what the heat pumps are capable of and implement really any of the designer's wishes based off their specific application. So yeah, summarizing the tiers of controls, we have the internal interface where the heat pump's doing all the work, the heat pump and the BMS interface where the heat pump's still doing the work, but it's reporting to this building management system. And then we have an external interface where the heat pump is basically blind to the rest of the system, but it's just being told when to turn on and off. And Jackson, I mentioned, is this third option of the external controls. So you can see the Colmac here is there's a control wire being ran to the Colmac that you can't see pictured, but it's being sent to this control panel that is then monitoring the tank temperatures separately. So we have a web interface that looks at all of the temperatures that this control panel is seeing, as well as the heat pump water heater statuses. And then all the heat pump water heaters see is whether they need to turn on or off. And with that, I'll pause for questions. If you have any specific questions about controls or how they might implement into different designs, I can address those here.
Yeah, Evan, actually an interesting question from Wes on what special skills or certifications are needed to repair and maintain CO2 heat pump water heaters?
Yeah, good question. That I actually don't have a specific answer to. We haven't dealt specifically with repairing CO2 heat pump water heaters. So as a refrigeration technician, you have to take tests on specific types of refrigerants, but I don't know if CO2 is actually included in that because they have really high pressures, right? So you want to make sure the tech knows what they're doing so they don't, they could potentially cut their arm off if there's a leak in the system, right? So it's a big risk. So I think, yeah, as part of the maintenance plan, it would be good to reach out to some service contracting firms and see, okay, what's going to be the cost of maintaining this equipment? If you do have to repair it, do you have the right certification to do so?
Yeah, and so that is specific to, CO2 because of that high pressure. That's really interesting. Those are all the questions here. I love this one. What could possibly go wrong? These are complicated systems, right?
Yeah, I think I'm getting the hint of sarcasm through there, but so I won't answer it directly. But yeah.
No questions right now on controls though.
Great. Yeah, so to sum up controls, really everything we've talked about so far, you need a really open dialogue between the manufacturer and the engineer and the installer to make sure everyone's on the same page and that they're getting the right information to accommodate the heat pump specific needs. Okay, power goes out. What happens to the hot water system? Does it still deliver hot water until it runs out? And what about with electronic mixing valves? Yeah, so we'll start with thermostatic mixing valves. Everything is still at city water pressure. So it would still deliver as much hot water as needed based off how much hot water is left in the tanks. Of course, the heat pump's not going to heat the water if there's no electricity, but there's still that large volume of stored hot water. So I would argue, compared to a gas system, where most gas boilers still have these electronics required for their controls, a heat pump system will actually deliver hot water for a lot longer because they inherently are paired up with more hot water storage. Electronic mixing valves usually default to the cold setting, where they have like a normally return to cold as soon as the power goes out. So then you would get cold water there. So that's a downside to electronic mixing valves for that reason. But they differ in how they operate. So there's some that's, I won't go too deeply into it, but it's a good question for the valve manufacturer on what happens when the power goes out. But yeah, great question. And so the next step in this, after we've determined the heat pumps we're going to use and the storage we'll pair with it, as well as the controls and the mixing valve and all of the smaller components, is we're going to get the submittal signed off. by the engineer and review those with the manufacturer, who is usually providing this submittal information anyways. So here's an example of a submittal from the heat pump water heaters at Jackson. So there's some important information here that you want to make sure lines up with the original design schedule, which is the equipment supplied as the designer understands it. Right, so we have the model of the heat pump water heater, as well as the design temperature and the heating capacity that it will operate at that design temperature. So we also have the COP that the designer was assuming when doing any energy modeling or anything like that. And something really important here as well is to verify the voltage and the electrical load associated with these heat pumps. Since manufacturers are always coming out with new models, sometimes these different performance values can be tweaked as the model moves forward. So the submittal information that you're sending to the engineer might have different information on it or different values than what the original engineer specified the equipment based off. So you want to make sure you verify all these numbers to make sure your building actually has enough electrical capacity to supply these, as well as the heat pumps having enough capacity to supply the building's hot water load. Oh, and here's a blown up version of all these really important things to have in the schedule as a designer and to verify with the submittal information as an installer. And so after the submittals have been submitted and all the details have been worked out, now it's time to verify and purchase the heat pump water heating equipment. And oftentimes there's a pretty long lead time between the submittal creation and the actual purchasing of the equipment. The engineer has to sign everything off and then the project has to gestate. But you want to make sure, again, you're working with the rep and the manufacturer to verify all the information you can in case anything has changed. Right, so there's usually a sales rep that's operating between the customer and the manufacturer, and the level of information that sales rep has will vary pretty greatly depending on their relationship with the manufacturer and how many other lines that they're carrying and how much of this product they've actually sold. Right, a sales rep might sell 20 different pieces of equipment, and then that manufacturer could be a very small portion of what they work with on a daily basis. So if there's questions you have that your sales rep is not confidently answering, I would highly recommend that you get in a group call between the sales rep and the manufacturer, because the manufacturer's engineers are working with this product on a daily basis or all day and answering any questions that come forward. So they definitely have the highest level of information, while the sales rep can still come up with or pass on the greatest really high fraction of information that you need. There's those little golden nuggets that the manufacturer might only have while you review your design and your submittals and the little details you need to make this equipment work. So the documentation you might want to bring to the manufacturer during this call is a lot like the documentation you need when you're reviewing the submittals. So sequence of operation is always great to run by the manufacturer to make sure that their heat pump to make sure it accommodates their heat pump's needs, as well as the plumbing schematics, the equipment schedule, control schematics, and the submittal documents. So if all of these align with what the manufacturer understands as accommodating their equipment, then you're going to run into a lot less problems down the road. And a lot of times the manufacturer can make really simple recommendations at this stage that aren't going to cause any big budget changes. Like, for example, just the removal of a check valve can make the difference between a system working and not working. And so when you're actually purchasing your equipment, you want to make sure that any purchase orders that you bring forward specifically lay out any additional options that are needed with that equipment. So then there's no miscommunication between the purchaser, the rep, and the manufacturer during this order. Even if you've worked with one person that knows this equipment really well from the rep agency, the minute you send in a PO, that might be received by somebody else in the purchasing department that has, hasn't dealt with any technical details of this equipment. So if you have a really good standing with one person, that might not mean that all of your needs in that purchase could correctly get relayed to the manufacturer through someone else in that agency. So you want to make sure that that's really clearly laid out on your purchase order and matches your submittal documentation. So for example, in the Colmac example for this case study at Jackson, we had a compressor warranty and a VFD ordered with the unit as additional options. So the contractor needs to make sure that they list specifically that there's a compressor VFD and a compressor warranty on the purchase order, so they don't have any complications during installation, as well as any issues once they receive the equipment if it's different than what they expected. So if there's anyone else that has gone through this purchasing process and can think of any details that maybe I've missed or anything they want to reiterate, this would be a great time. I would love to hear your feedback on what details have been important to you during this process.
Yeah, I'm curious, especially because at the beginning we had several folks saying that they had gone through this process. So I'm wondering if they would be willing to share some advice.
Yeah. I know there's this weird waiting period sometimes with Slido as you're waiting for people to frantically type in their answers.
Well, we can wait for a little bit. Yeah, I'm always curious. I really do love to hear from folks. Some really interesting conversations. Obviously, Evan, you've been part of those too, getting feedback from folks in the field, and new insights, new ways of thinking about it, or new problems, or, oh, I hadn't thought about that, or whatever. All of those pieces are really illustrative for our team as well when we're making the education that's supposed to feed that need. It's really interesting.
Yeah, it seems like every person on every design or installation job has kind of a unique perspective and something that they've learned themselves. So anything that people can share from that and just kind of expand this wealth of general knowledge is super important.
Maybe this person is the same ironic person, the author of that ironic comment earlier. This is hilarious.
Yeah, I like this. I like this person. This is very accurate sometimes too, right? You need to give, exactly the information on the purchase order that can be forwarded on to the manufacturer a lot of times, and really, really straightforward information.
Yeah. I want to ask about this lead times OMG comment, because I know that supply chain issues are kind of rife right now throughout everything, right? Everybody's having supply chain issues. What do you know about the commercial heat pump water heating supply chain issues here?
Yeah, it really there's so many different portions of the chain that could exacerbate these lead time issues that the capital OMG really lays out well. But yeah, there's the fact that the raw materials are hard to provide to these manufacturers of all the individual components that go into the heat pump, and then some of these manufacturing chains, those manufacturers have been backlogged as they've been closed down due to COVID issues, as well as we have an extremely quickly expanding heat pump water heater market that these manufacturers are trying to keep up with. So they're dealing with a combination of more orders than they've ever seen before, and a production capacity that has been tuned to these earlier projections of orders, in combination with not being able to receive the components to actually put their heat pumps together. So it's kind of a double whammy that's not very fun to play with.
Yeah.
yeah, it's
There's a
really
comment
important.
during 6 months of wait time. Yeah.
Yeah, and I don't know how different it is depending between the different manufacturers, but that's something that you'll want to ask the manufacturer during the submittal process. Like if you're a project manager and you think this job's going to be done in 6 months, you need to check with the manufacturer that they have a really short lead time on their equipment, or else that could push the entire project out by, at least 6 months.
Yeah. Really, this is a big deal. Yeah. All
Yeah.
right. Thanks.
Yeah, I'm glad we waited because these are great comments. Okay, now we've laid out all the details and we've purchased the equipment, and now it needs to be installed. So a piece of advice I've had that I couldn't hold out until this point, so you may have heard it a couple times already, is maintain an open dialogue with the manufacturer and engineer during the installation. So it's really important that first of all, you have all the information you can get, and you've kind of gone through the installation almost in your head or in a manner of preparation with the manufacturer, but you also need to make sure that they're available to answer any questions during the installation that may have been overlooked during the design and planning process. So if possible, let your contact know ahead of time what the actual installation schedule will be, so then they can anticipate any questions that can come in. And so the three big pillars here to consider when you're installing equipment is communication. You need to ensure correct installation to ensure reliable and efficient heat pump water heater operation. And you need to remember that this is not a gas water heater, so any best practices that you have with that need to be carefully considered. And so I talked about talking to the manufacturer to get installation details, and just make sure that you have really open communication with them, because there are, like I mentioned, those little gold nuggets of information that you can get from the manufacturer that might not be found in the submittal data. And I've seen a lack of communication up front lead to a lot of problems that really dragged out after the fact, right? Because if something's installed and the heat pump's kind of working, but not exactly how the engineer imagined it would, there might have been really easy changes to be made ahead of time that retroactively are going to be a really big pain. So the first part of making sure that you have correct installation is to make sure that the whole team's on board with what the design looks like and the considerations that you've learned in talking to this manufacturer. Because if there's one person on the team that knows everything about heat pump water heaters, but that knowledge isn't passed along to the rest of the team, then it's not going to be useful for that one person knowing everything when they're not doing every little piece of work to the system. And a big point here is that heat pumps are not gas water heaters. So you want to make sure that any best practices that usually don't shine through on designs, you want to make sure those actually apply to heat pump water heaters, because installers that have been working on these for decades have found a lot of really great tricks to use or ways to enhance plumbing designs that aren't quite as evident to the engineer or shown in the drawings, but they don't even, they don't communicate with the engineers on these little changes that usually make these systems better. There's certain things, though, that with heat pump water heating systems, if they assume the same thing, then that could totally make the system fall on its face. And one example I've seen here with Colmax heat pumps is they often pair the cold water line going to the heat pump together with the domestic cold water line going into the tank. So this line has the potential to bring in cold water when there's building usage, but the heat pump also uses this line to pull cold water out of the tank. So if you were to put a check valve on this line, as plumbers normally do on the inlet of a tank, now that heat pump can't pull that water out, and it's not going to be able to rush water through its heat exchanger and get rid of that heat. So the heat pump's just going to go into alarm and say something's wrong here, because this check valve that wasn't actually on the drawings has been added by the installer as a best practice. So I'm definitely not saying to get rid of all your best practices, but if it's not on the design, then definitely check in with the designer to make sure that it's not compromising the system itself. And so after going through all this, I want to take a quick pause and see if you've gotten any solid takeaways from our conversation on installation. And again, if there's anything that I've totally glazed over where you're thinking, wow, this part of installation is really important, maybe we should cover this, definitely bring it up here.
Do you have any stories to share, Evan, about any installations that you were involved in that would either be funny or illustrative in some way?
Yeah, I mean, so I did a lot of heat pump startups for Colmac. So I was the person on the ground telling people whether the heat pump's actually going to work or not if they hadn't been talking to us. So I definitely experienced a lot of issues with how things were installed because the installer was just, maybe they either didn't think about it or assumed heat pumps were going to work slightly differently. So the check valve example I used, probably 5 or 6 different startups had that same issue. So that was an easy thing. But I mean, once you have to remove that check valve, that means draining the entire system and cutting the piping open and then getting any copper remnants out afterwards. So it's a big issue actually removing it. And then the second most common thing I would say is the placement of these sensors. The electrician has the high voltage wired up, the plumber has all the plumbing in, but nobody thought about, or nobody thought it was their scope to install these sensors that are telling the heat pump when to turn on and off. So I get there to start the heat pump on, and the sensors are coiled up in the electrical cabinet. So there's not really a way to ensure that the system's going to work. Right? I can tell the heat pump to turn on and heat water, but it's not going to ensure that we're actually going to have a working system.
Wow. And those are small pieces, but super important.
Yeah, right. And they can really cause a big delay if they're not thought about ahead of time when they're
Exactly.
Yeah.
Okay. Looks like we've got a lot of takeaways from installation. I'll let you get to those. Thanks, Evan.
Yeah. Yep, best practices are a big deal. And the check valve example, yeah, it's very important. Make sure the manufacturer and engineer are involved in the install. Yes. Yeah, that should be reiterated several times if you haven't caught that from me. They definitely need to be involved in the install and throughout the entire process, and especially if the installer is not 100% familiar with heat pump water heaters. And then there's a question about commissioning and startup to confirm proper operation, and that's the next thing we're going to dive into. So that's a great segue. And if in doubt, ask. That's a big thing that we need to make sure to keep in our mind as well. Nobody knows everything, so it's better to ask questions than assume that you know what's going on and have to change something later. So after we've installed the equipment, we can go through the startup process, right? And this is to ensure that the heat pump water heater as installed is actually going to operate efficiently and reliably. So usually the startup is done with heat pumps. It's usually done by a factory technician to confirm all the settings and make sure the heat pump's operating as expected. And oftentimes there's a commissioning agent that comes in after that to do functional testing on the entire system and make sure they're seeing what they expected as part of the design. So when scheduling startup with these technicians and engineers, you want to make sure that you schedule it as far ahead as possible. And I understand there's this weird balance between scheduling something so soon that you don't actually know if you're going to be complete, and scheduling something so late that none of the techs are actually available that day. So there's kind of that sweet spot where if your project is going really smoothly and you've made all of the communication, then it's good to schedule, say, 3 or 4 weeks ahead of time when you're confident that the system's going to be up and running. So in the technician, there's going to be a kind of a variable rate sometimes, depending on where the factory technician is coming from, whether they have to fly and those costs have to be covered by the actual startup costs, or if they're right down the road at the rep agency. So that's a good thing to keep in mind. I mean, even when you're bidding a job, what it would cost for the startup operation of these heat pumps. And then to avoid some startup hurdles, you want to make sure that you have really open communication between all the different trades, because heat pumps are in this kind of weird realm where they have the plumbing contractors typically buying the unit, but they also need to coordinate with the mechanical contractor because they're hiring or handling large volumes of air, as well as high voltage electricians because they're powered with 208 or 230 or 460 volt power, as well as low voltage because they need to wire all the sensors to the tanks and things like that. So all of these different parties need to be in cooperation and have an open dialogue to make sure that scheduling is going well and that every part of this system actually has somebody that knows that they're taking care of it. And so with that, what questions remain based off startup or really any details of this system? We're kind of coming to a close here, so any final questions that I can either reiterate or provide more detail to would be really helpful.
Yeah, nothing yet in the Q&A bar, but that doesn't mean that folks aren't typing.
Right.
Just to jump ahead just a little bit, Evan, as we do wrap up, we've got one more session in this series, correct? And it's 7 days from now. So this time on the 17th. Can you talk a little bit about session 4?
Yeah, in session 4, we'll be talking a lot more about some different installation details. So maybe this would fit better in the context of all 4 sessions. So we're talking about, first we were talking about why use heat pump water heaters in general, maybe talking to the developer or the architect that wants to implement these. And then we transitioned to talking about how the designer is going to implement that once we've understood why heat pumps are going to work in this system, right? And then the baton is kind of passed to the contractor installer. And this session we talked about how we're filling in any little details on how to bring this design to installation. And then the last place we're going to pass that baton is to the building manager or the service contractor or any closing sections in installation where we want to make sure the heat pump actually operates for a long time down the road. So we've kind of taken the heat pump water heater through this entire process from top to bottom, and now next week we're going to talk about the maintenance things that you need to think about to make sure it actually operates long term.
That's awesome. Great. So the full cycle, the full Mary Ann from start to finish. That's great.
Yeah, that's what I really like about this series is we've been given enough time where we can really take it through the whole process and give people a big picture idea of what's going on, through the whole process, because it's really important not to wormhole on any of these issues because it always affects the next step down the road and even the previous step in the next design or the next project.
Yeah. No questions, looks like, except for a funny one from Ian says, "What's that cubby you're sitting in there?"
What's the yeah? So
you're sitting in your
I call
cubby.
this. It's interesting. I call this my mobile office because I live like I said, I live in the northeast corner of the state, and where I live, it's a beautiful area, but internet's just awful, right? So I have satellite internet at home, and it's not up to video calls. So my mobile office is located at my friend's house that I met through Colmac, and who has great internet a little ways down the road. So I
There
go to
you
my
go.
mobile office when I need to make video calls, and it's pretty comfy in here as long as the heater's working well.
Great. All right, let's finish up, Evan. Thank you.
Yeah, so heat pump water heaters for hydronic heat. That's really, yeah, that's a big subject. And there are different limitations when talking about using hydronic heating with heat pump water heaters, because we're heating warm water up to a higher temperature. So it's, you know, a totally different set of limitations because of the different temperatures they're dealing with. So the specific question here is, we have a hydronic loop serving water to air heat pumps served by boilers and an equally aged cooling tower. Could we replace all that with an air to water heat pump? Yeah, and so hydronic loops are usually designed for, say, 160 to 180 degree water. So it's tricky to have a heat pump work directly for that. But with some upgrades to the heat exchangers and the heating and cooling, it's possible. So I'll probably leave it there, because I could talk a long time about heat pump space heating, but I don't think we have time here for it. And are there particular things we should look out for in the commissioning process? Yeah, so there's kind of a big checklist that you can think about in terms of looking at different water temperatures and how the heat pump's operating. And different manufacturers will supply different information on how their heat pump's supposed to operate, as well as how it's reporting its current operation. Right, so you need to, if you can believe I'm going to say this, you need to work with the manufacturer to see how do we check that this heat pump's actually operating optimally. And then on top of that, you need to just do the same things that you would to commission a gas system, and making sure you're getting proper temperatures to the building, as well as making sure all the equipment's turning on and off when you would expect it to, based off the sequence of operations. So it gets pretty specific per manufacturer, but in a more general sense, it's just making sure you're following the sequence of operations and the equipment's turning on and off as you would expect. Yeah, and I think that's really all we have today. We talked about these 4 steps in the transition from the design to the operation of the heat pumps, and finding your contractors and what attributes are ideal for an installer, as well as determining the details you need to get ironed out with your equipment during the planning and the verification and purchase process, and some key aspects you need to think about or keep in the back of your mind while you're doing installation and startup on this equipment. And hopefully I've helped answer the question of how do I choose the right equipment, as well as what steps do I need to take to implement a commercial heat pump water heater system. So that's all I have for you today, but as Lauren mentioned, we do have session number 4 next week, and that would be on November 17th from 10 to 12 p.m. So you can sign up through the Seattle City Light, the Lighting Design Lab, and then we can talk about how to properly maintain this equipment and what to think about there.
Excellent. Hey, Evan, it's just such a pleasure to be here. Thank you so much. We've got a lot of thank yous in the chat, and how great your information was today. So our thanks, of course, our gratitude goes out to Seattle City Light and the Lighting Design Lab for having us. Evan, to you and the EcoTip team, just always such a pleasure to work with you, super informative. And to everybody on the call today who joined us in this session, we hope to see you next week on the 17th, same time. So we'll sign off today. Thanks to everybody. And this session should be posted in the next couple of days on the Lighting Design Lab website. So feel free to check that out and pass it along to your colleagues who might need this information as well. Thanks, Evan.
Yeah, thanks everyone for coming, and thanks Lauren for moderating this. This has been great.
Great. And thanks to Armando and the great team at LDL. Bye-bye, everybody.
Thank you all. Have a good day, everybody.
Bye-bye.